Good afternoon. I appreciate the opportunity to be with you today. My presentation today is mainly on the subject of learning on temporal heterogeneous graphs with supplementary information from LLMs. First off, I will briefly introduce the background of my research. Extensive works have been dedicated to graph learning in both academic and industrial communities, owing to its powerful capabilities of mining and discovering abundant information in the non-Euclidean space. As we all know, a typical graph consists of nodes and the edges that connect them. However, general methods consider these graphs to be static. As the saying goes, nothing is eternal except change itself. In the real world, most graph systems are usually dynamic and constantly change over time, making temporal graphs ubiquitous. In such temporal graphs, the topologies evolve as nodes and edges appear or disappear across time, along with the attributes of nodes and edges changing dynamically. Moreover, real-world scenarios generally involve heterogeneous relationships. When we introduce heterogeneity into a temporal graph, it is called a heterogeneous temporal graph, abbreviated as THG. This means that the nodes and edges belong to different categories. A temporal heterogeneous graph has been viewed as a series of evolving heterogeneous graph snapshots, along with a node type mapping function and an edge type mapping function. Here I have shown their formula definitions. THG data provides a fundamental and accurate abstraction of real-world networks as they have rich semantic, topological, and temporal information. Learning on THGs has received substantial research attention since it can be applied in a wide range of scenarios like recommender systems and other information retrieval fields. Next, I'm going to talk about the motivation of my research on THGs. My primary motivation for this work is to design a multi-level learning framework for THG data. There are two reasons. First, graphs across different domains generally have their own unique characteristics and evolution patterns. This picture illustrates two examples of temporal heterogeneous graphs in different domains. We investigate the frequencies of interactions occurring between different types of nodes, and they exhibit specific evolution patterns. Thus, it is necessary to learn the overall nature of THGs at the graph level. Second, the heterogeneity of THGs implies that different types of nodes have varying properties and change over time following independent processes. So learning at the node level may make the learned node representations drop much latent information, and only constructing graph-level features leads to the neglect of the heterogeneity of graphs. As a result, representation learning for different node types and the whole graph are indispensable. In this work, we designed specific aggregation strategies for learning at different levels. In addition, by harnessing the superior power of large language models and LLM-based embedding models, our method effectively enhances the multi-level representations. By refining the diverse properties implicit in summaries generated by LLM, we can integrate LLM-based external knowledge. The LLM-based enhancement brings some benefits as demonstrated. Next, I will describe our method in detail. In this work, we aim to address the aforementioned issues by proposing a cascaded multi-level learning network abbreviated as CASMLN for THG. Here is the overview of our method. It mainly consists of 5 parts. Next, I will introduce them one by one. Prompt-based learning provides textual instructions to large language models, which allows LLM to adapt to distinct tasks and various data domains. So we also utilize the power of prompt LLM and LLM-based embedding models to learn the relevant external knowledge for THG and integrate it into type-level and graph-level representations. We first construct a brief text-based description of the graph and an instruction that requires output in a fixed format, treating them as the prompt for the whole graph and node types. Examples of prompt construction can be found in this picture. In each time slice, we first apply relational graph convolution to basically aggregate information from neighboring nodes of different relationship types. In order to distinguish the data for each relationship type, specialized transformation matrices for different types of relations are assigned at each convolutional layer. In graph theory, degree centrality is a significant criterion to measure the importance of nodes in the whole graph structure. Node degrees help to discover influential nodes in a network. For a given node type in a heterogeneous graph, nodes with higher degree tend to have a stronger ability for information transmission and are more critical to the graph topology. Therefore, we devise an aggregation strategy based on the degree centrality to generate type-level representations for heterogeneous graph snapshots. The LLM-based representation vectors are also integrated for type-level representations. As for the graph-level learning, once the type-level representations at T are obtained, a weight that reflects the importance of each type-level representation is learned through a linear layer. We aggregate all the type-level representations through weighted averaging and also integrate the LLM-based vectors to generate the graph-level information. To fuse the multiple levels of representations, we use learnable weights. We explore a concise attention approach to capture deeper temporal patterns among continuous time steps in the entire historical graph sequence. The normalized attentional scores are then used to fuse all the sequential representations so as to achieve the final node embedding used for prediction. Next, I'm going to talk about the experiments. We totally used 4 public real-world THG datasets for evaluation. The statistics of datasets are presented in this table. All datasets come from completely different fields. And the downstream tasks for evaluation include link prediction, node classification, and node regression. Baselines include static or dynamic as well as homogeneous or heterogeneous graph learning methods. This table shows the results of performance comparison. And the results indicate the effectiveness of multi-level learning structure and LLM-based enhancement. These 2 tables present the results of evaluation study. Removing any component of custom LN results in a performance degradation, where the removal of the multi-level learning results in the largest performance degradation. This corroborates the validity of our motivation for designing the multi-level learning structure. In addition, ignoring graph-level or type-level information leads to different degrees of performance drop on different data sets, which is attributed to the fact that diverse THG datasets have distinct needs for representational information at different learning levels. To further compare the efficiency and scalability of different methods, we count the average training time and the maximum GPU memory consumption during training. As we can see, if we ignore the overhead imposed by the LLM, Custom excels in both training time and memory overhead. This implies the better efficiency and scalability of our method, which is mainly due to the simplicity of our multi-level aggregation and temporal attention. For the hyperparameter investigation, we studied the impact of graph convolutional layer depth amplification factor used for degree centrality aggregation and the embedding dimension. We further analyzed the temporal attention coefficients and evolving embeddings at multiple levels through visualization. The results and findings demonstrated the unique patterns of change across different graph domains and node types. This aligns with our motivation for applying multi-level learning to THG. To get more intuitive insights into our method, we conduct a case study on the ecom dataset as shown in this figure. Overall, there is a significant difference between the link probabilities output by CustomLM for real and fake edges, but this is ambiguous for CustomLM without multi-level learning. Based on the case study, we can confirm the effectiveness of our method and the benefits of incorporating the multi-level learning structure. Lastly, I will provide a conclusion and offer a perspective on future work. So in a nutshell, our major contributions include proposing a multi-level learning approach on THG, the exploration of combining THG learning with LLMs, and as well as the outstanding performance and efficiency of our method. As for future work, we will try to design more refined aggregation methods for multi-level learning on THG. We will also attempt more LLM models and explore more methods of introducing external knowledge like contrastive learning. Furthermore, we will specifically try to improve scalability for application in large-scale temporal graphs. And lastly, here is my contact information. If you have any questions, feel free to contact me. That's pretty much it. Thanks for your attention.